This is the third tutorial on the structure of output files that Petrolog saves on disk, and this tutorial considers the most complicated and complex case when the starting composition has trace elements and volatile elements, and we also use distribution coefficients to define trace and volatile elements in all phases. So I've set up parameters here which you can see include olivine, plagioclase and clinopyroxene from the silicate minerals. It also includes sulphide, fluid and sulfate models. We have variable extent of fractionation for the phases, and before we start I would like to highlight for you that for this particular output on screen we'll be using components, which effectively means that we will be using oxides to represent compositions of major and volatile elements. So let's start the calculations, and then I will pause the video until the calculations are completed. I'm starting it now. The calculations are now completed, and I would like to start with looking at the calculation parameters which are reported at the start of the calculations, and in particular to look at the trace elements and volatile elements which will be defined using distribution coefficients. And you can see that in this case we use distribution coefficients for sulfur between the silicate melt and fluid using the model of Ding et al. 2023. There are also some other models, and as you can see there are some constant values being used for some of the elements. As we discussed with you before, the output starts with phases present both in the magma, which is shown on the top, and in the cumulate, which is shown on the bottom. The first mineral to crystallize in this particular case is olivine, and very quickly it is joined by plagioclase, and the two minerals crystallize together. And then when the crystallization extent reaches 9% in this particular case, we have sulphide joining the crystallizing assemblage. So we are forming sulphide, which is present both in the magma and in the cumulate, because we said that sulphide is fractionating 50%, half of it goes into cumulate, half of it stays in the magma. And what I would like to bring to your attention is that as soon as this happens, the composition of the magma, which is a mixture of all the phases present in the magma, is now displayed in elemental concentrations, even though we wanted to display the concentration using oxides. The same is true for the cumulate. The cumulate itself, now the combined composition of all the cumulate phases, is shown using elemental concentration. This is simply because when either fluid or sulphide melt are present in the magma or cumulate, it is simply impossible to show the combined composition using components, because there are different components present in these phases. So you can see here we have iron S, and iron is combined with sulfur, and here there will be sulfur which is combined with nickel and copper for the sulfide. When we continue crystallization, at some point later on we will have fluid joining the crystallizing assemblage, because the composition has become fluid saturated. And again, the fluid has different components. In this particular case we have H2S and SO2, and these are not present in other phases. So as a result of this, just to summarize, we have each phase shown using components as was selected by the users by us, but the combined concentrations in cumulate and magma have to be shown using elements. So as soon as either sulphide or fluid has appeared, we switched from oxides and sulphides to elemental concentration, and that will be continued until the end, when also Kleiner pyroxene joined at some point the calculations, and that's the final state after 50%. Now these are the files which were saved, and if we load them into Excel, what we will see with you that the composition of magma again is shown using elemental concentrations, whereas the composition of melt is shown using the oxides as was requested, and the compositions of all individual phases are shown using components as we requested. So this basically is the main take-home message from this video, that if you have those complicated scenarios, even if you would like the results to be reported as oxides, the combined compositions such as magma and cumulate will be reported in elements. Personally, I feel that this is a very complex and difficult to understand a type of output on screen, so when I do calculations for my own purposes for compositions like this, I would rather go to options and say that I don't want to use component for screen output. So let's have a look how the results will look if we, for this particular case, choose using elements to display concentrations. I'll start calculations and we will look at it once they have finished. The calculations are now complete, and this is how the output looks at the end when we use elements for displaying the results on screen. In my view, this is a much tidier way to represent the results, as in every phase the same columns are used, and the only comment I would make here, remember that positively charged sulfur is +6 in melt and any of the silicate phases if there is sulfur present, but in the fluid it will be +4. This is the end of this video. As always, if you have any questions, you can email us to support@petrologsoftware.com.